Okay, hello everyone in a new video. Then we have reached part 2 of chapter 9, which is the chapter of equilibrium of a body in the third unit of mechanics. And in this one we have reached section number 5, which is Hooke's law. Till this moment regarding chapters 8 and 9 we didn't discuss any law. So far we have only discussed the condition of equilibrium. Now we are going to introduce Hooke's law. And then in order to do so, let's consider the adjacent document. In this document we have a spring R of a free length L0. So L0 is the free length of the spring, and this can be measured using a ruler. The spring is connected from one end to a fixed support, whereas the other end is a free. Now suppose in this case, for the same spring, we connect a solid S from the other end, and in this case the spring will elongate to a new length which is given by LF, and we can define the elongation which is set to be delta L. Then let me write here that delta L is equal to the new length, which is the final length, minus the initial length. Now if you consider the solid S here, what are the forces acting on the solid? We know that one of the forces is the tension, because we have a spring, and the other force is the weight. We are interested in discussing how does the value of delta L depends on the solid itself and the type of the spring, and this is known by Hooke's law. So let me write Hooke's law here. Hooke's law states that the tension in a spring is proportional to the corresponding elongation, and later on in the next section we will consider also the case where the spring is being compressed. So let me write between brackets compression. So in this case we are in the case of the compression elongation. Then let me write section 5.1. Elongation of a spring So referring to Hooke's law is stating that the tension in a spring, so let me write T corresponding for the tension, is proportional to the corresponding elongation. So proportional, what does it mean? If we construct the triangle, suppose that T is at the top, for example, we don't know if T is at the top or at the bottom, but since we are talking about directly proportional and proportionality, so proportional itself, here proportional, if it's not stated whether inversely or directly, so this is taken as directly proportional. So now referring back to this, so because T will be directly proportional to the elongation, then T must be here and delta L must be here. And in this case the proportionality constant is given by K. So this is the new formula corresponding to Hooke's law. So here let me write as a title, according to Hooke's law. And we know that for any formula in physics consisting of three variables, we can construct for it or set up the corresponding triangle. Then here, because we have multiplied, then t will be at the top, k and delta L at the bottom. Suppose, for example, we are interested in determining k, then k is given by t over delta L. And recall that delta L is the elongation. Now I will introduce what is meant by k. If you are interested in determining the value of delta L, so covering delta L with our hand, then delta L is given by t divided by k. So there are two different methods to calculate delta L. One can calculate delta L by referring to this equation or by using the ruler, by measuring the initial length and the final length, and delta L is said to be the difference between the two lengths. So let me say where T is the tension in the spring. Previously, we used to calculate the value of the tension in a string, not a spring, by referring to, so not all, okay, we can generalize this. Previously, T used to be calculated for a string or even for a spring by referring to the condition of equilibrium, but we didn't see any explicit relation that one can directly determine T from it. Now, if we are dealing with a spring and we know its stiffness and we can measure the elongation, then the value of T can be directly calculated from this explicit relation, and this is very similar to Ohm's law in electricity. Now, because T is the tension in the spring and it corresponds to a force, then for sure its SI net is given by capital N, which stands for Newton. And graphically, the tension T is the force existing along the spring. Now, as for K is a property of the spring itself. So K is said to be the stiffness of the spring and its SI net is given by, then if we refer to this triangle, if this is in newtons and this is meters, then covering our hand here, then the unit of K is given by Newton per meter, which stands for newtons per meter. And delta L, then recall that K is the stiffness of the spring and K is a property of the spring itself, similar to the resistance. For each resistor is being characterized by resistance R, then each spring is being characterized by stiffness K. Then delta L is the elongation of the spring, and we know that the SI net of distance is, or length is meter. Then this is meter. Now let me also mention the following note regarding this equation. Now this is a linear equation, but now here what I have considered is that delta L is the unknown, but at the same time you can consider, for example, LF is the unknown, where delta L and L0 are given. So in this case, for example, if the final length is unknown, so we have that delta L is equal to the final length minus the initial length. Now dragging the final length to the left hand side, so it will be minus the final length, and dragging delta L to the right hand side, it will be given by minus delta L minus L0, and multiplying everything by minus sign, then we'll have that the final length is equal to delta L plus L0. So what I have done here is just a rearrangement of this equation based on the fact that the final length is the unknown. Now we can do the same if we consider now the initial length is set to be the unknown. Then in this case we can write that delta L is equal to the final length minus the initial length. Now dragging the initial length to the left hand side, it will gain another minus sign, so it will be L0. And dragging delta L to the right hand side, it will gain a minus sign, it will be minus delta L. So in this case the initial length is given by the final length minus the elongation delta L. So this is it regarding the elongation of the spring. Now we can also consider an interested case in which the spring is being compressed. So let me write the title of this section, which is 5.2 compression of a spring. Now here in the following document, so also we have a support, but in this case you can consider the support to be a table, and in this case the support is a ceiling, for example. So now the spring is placed on the support, and this is the free length of the spring, in which here there is no mass connected to the spring. Now in this case we place a solid S having a mass m on the spring. We know that one of the forces acting on the solid is the weight which is acting vertically downward like this, and here you need to be careful that what is the direction of the tension and the line of action. So the line of action will be always along the spring, something like this, but in this case recall that always the tension is trying to oppose the effect of the weight which is vertically downward. For this case the tension is vertically upward. And here, so this is the initial length L0. After we have placed the solid S, the spring compresses to a final length which is given by LF, and here delta L, for sure it can be calculated using Hooke's law, as we shall see now, but using a graduated ruler one can determine the elongation. Here delta L is said to be the compression and not the elongation, and it can be calculated using the following formula: initial length minus the final length. Okay, so if we refer back to the case of the elongation, notice that in the case of the elongation it's given by the final length minus the initial length, because LF is greater than L0 because the spring is undergoing elongation. But in this case, because the spring is undergoing compression, so the initial length is greater than the final length. For this reason delta L is defined as the initial length minus the final length, and this for sure can be calculated using Hooke's law. Then let me write down according to Hooke's law. T is equal to K multiplied by delta L. So here nothing is different, it's exactly the same. And as we have said previously, any formula in physics consisting of three variables, we can associate to it a triangle. Here, because we have multiplied, then T will be at the top, K and delta L at the bottom. For example, if you are interested in determining the value of K, then K is given by T over delta L. If you are interested in calculating delta L, then delta L is given by T over K. And now let's redefine what does each quantity represent with its corresponding SI unit. Then let me say where T is the tension in the spring, K is the stiffness, of the spring, and recall that its SI unit is given by Newton per meter. And previously delta L is said to be the elongation. In this case, delta L is the compression of the spring. And its SI unit is given by m, which stands for meter, because the compression is something which is measurable using a graduated ruler, and length is always given by meters in the SI unit. Okay, recall that, for example, in order to convert from centimeters to meters, we divide by 100, for example, or from meters to centimeters, we multiply by 100. But what is important, that the SI unit of length is given by meters. Now, as we have done previously, let's consider the following equation, which is delta L is equal to L0 minus LF. Now, if L0 is promoted to be a variable instead of delta L, and delta L and LF are constants, then delta L is equal to initial length minus the final length. Then dragging initial length to the left hand side and delta L to the right hand side, we have minus initial length is equal to minus delta L plus, minus the final length. In this case, if you multiply everything by minus sign, then L0 is given by delta L plus the final length. So let me write this equation here. Now, for example, if we promote LF to be a variable and delta L and L0 are to be constants, now dragging LF to the right hand side, it will gain another minus sign, so minus with minus it will be plus. The initial length remains here, and delta L dragged to the right hand side, it will be minus delta L. So another equation can be added here, which is the final length is equal to the initial length minus delta L. And now let me add the following important notes. Or let me say before. Okay. Let's consider the following note. So notice that in this case, T and delta L are neighbors living in the same floor, so they hate each other. If T increases, regarding K and delta L, they are neighbors living in the same floor, so they hate each other, then they are inversely proportional. Now, what about T and K on one side, T and delta L on one side? They are directly proportional. So let me say T and delta L are directly proportional. So what does this mean? If T increases, delta L increases. If delta L decreases, T increases. T and K are also directly proportional. And as for K and delta L, I repeat that they are neighbors living in the same floor, so they hate each other. K and delta L are inversely proportional. So if K, for example, increases, delta L decreases. So recall that what does directly proportional means that they behave in the same manner, and inversely proportional means that they behave exactly opposite to each other. And now let's discuss the important notes. Then the first one to mention is that K the name of K, then K is a physical quantity characterizing the spring, and the name of K is given by the stiffness of the spring, or simply the stiffness, also known as the force constant. And an additional name for this one is given by the spring's constant, or constant of the spring. Now the second important note is to mention that K is a physical quantity, that characterizes the spring, so each spring will be characterized by a certain value of K. Now the third note that we need to consider is that L0 is named to be the initial length, and even sometimes this is given by the free length. And here the term free refers to that no mass is being connected to the spring. Now idea number 4 is that LF sometimes is given by the final length or length of the spring. And finally, delta L is sometimes denoted by X, which represents the elongation, and sometimes it's given by the compression if R is being fixed to a support like this. So these are the different notes that one can consider when discussing Hooke's law. And now let's solve the following exercise as a direct application on what we have explained regarding Hooke's law. Then section number 6, exercise number 4, they are telling us a spring R of stiffness K is equal to 20 newtons per meter. Then the moment we have the stiffness of the spring, it means that we are interested in Hooke's law. Is attached to a fixed support, a solid S of mass m is suspended to the free end of the spring in document 1. So they mentioned document 1, then now we can use it. Notice that in this case we are in the case of elongation and not compression. They are telling us that S is at equilibrium, so at any moment in this exercise we can use the condition of equilibrium under the action of two forces. We have the weight, we have the tension, and in this case we have the value of the tension, which is given by 1.5 newtons. Now before we consider the exercise, let's consider the given. We know the stiffness, we know the tension. One, for example, can calculate the elongation of the spring, which is X. Now they are telling us the following statements are false. So all of these statements are false. This is false, 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 and false. We need to rewrite them correctly. Then let's start by number 1. They are telling us the elongation of the spring at equilibrium is given by X is equal to 6 centimeters. Then the first thing that one should do is to locate the wrong part in this statement. So from here to here, we are pretty sure that nothing is correct. The correct part may be with this value. So first we need to determine the elongation X and to rewrite this statement correctly, because we already know that this is false. So the wrong part may be in this value. And we know that the elongation in this case, because we don't know the final length and the initial length of the spring, can be determined using Hooke's law. Then apply Hooke's law. Then we always start by the initial form, which is given by t is equal to k. Usually the elongation is either denoted by x or delta L. Because here in the exercise it has been denoted by x, let's use the same notation, and we are interested in determining the value of x. Then constructing the triangle of this formula here, because we have multiplied and t will be at the top, k and x at the bottom, we are interested in determining the value of x. Then x is given by t over k. The value of t is given by 1.5. And the value of k is given by 20. Now plugging this fraction on the calculator, then the value of x is given by 0.075. Since everything in the SI, so the value of x will be in the SI, which is meters. Recall that x represents a measure of length, and the SI unit of length is always given by meters. In order to make sure that this is in meters, making sure that we have replaced this in Newton and meter. Now T over K, which is a Newton over a Newton per meter, which is given by Newton over 1 multiplied by meter over Newton. So this cancels out with this, so the unit is given by meters. Now in order to compare this value with the value here represented in the statement, we cannot compare quantities in physics unless they have the same unit, so this must be converted back to centimeters, although the value that we have calculated is in meters. Then to convert from meters to centimeters, we multiply by 100. Then 0.075 multiplied by 100. This is equal to 7.5 centimeters, and for this reason, the statement is wrong. Now, as a part of the answer, we need to rewrite the statement correctly. Then let me write down that the elongation of the spring at equilibrium is x is equal to 7.5 centimeters. Now, as for number 2, they are telling us that W is a contact force and T is a force acting from a distance. We know that the only three forces act at the distance. They are given by the weight, the electric, the magnetic, and all other forces are classified as contact forces, and in particular the tension T. For this reason, this statement is false. Then let me say that W is acting from a distance. Whereas the tension T is a contact force. And we need to rewrite this statement correctly. Then W is acting from a distance. And T is a contact force. Now, number 3 is, since S is at equilibrium, then the relation between W and T is given by W vector is equal to T vector. Now, as we have done in number 1, the wrong part in this statement may be in this relation. Now, in order to determine whether this relation is, what's the wrong in this relation, let's refer to the condition of equilibrium and discuss what's the relation between W and T. Then let me say here as a title, at equilibrium, then on the left hand side of this equation, we will write the different forces acting on the solid S, and they are given by the weight and the tension. And on the right hand side of this equation, we write the zero vector corresponding for the condition of equilibrium. Now dragging T to the right hand side, it will gain a minus sign, then the W vector is equal to minus T vector. So the first equation, let's recall that it means that the effect of forces cancel each other to give us the zero vector, whereas the second equation means that both forces have the same line of action, opposite direction, and same magnitude. And if you compare this relation with the given one, you notice that here there is a missing minus sign. So the correct statement will be given by since S is at equilibrium, then the relation between W and T is that W vector is equal to minus T vector. And now as for number 4, they are telling us that the mass of S is M is equal to 2 kilograms. So the wrong part may be in this value. Then let's determine the mass of the value of M. In order to determine the mass, first we need to know the weight. The weight can be deduced from this condition. Then because we already know the value of the tension. Then knowing that W vector is equal to minus T vector, then how do we read this equation? Both forces have the same line of action, opposite direction, and same magnitude. We are interested in determining the magnitude of the weight. Then let's see in magnitude. Then we drop down the vectors and we remove the minus sign. Then W is equal to the tension. But we already know that the value of the tension is given by 1.5 newtons. Then weight is equal to 1.5 newtons. Now recall that we are interested in determining the mass and not the weight. So weight and mass are related via the following formula. Then constructing the triangle of this formula, here because we have multiplied, then W will be at the top, M and G at the bottom. Putting our hand over M, then M is given by W over G, which is equal to 1.5 over 10. Plugging this fraction on the calculator, then the value of M is given by 0.15. Since everything is expressed in the size of the value of W and G, then M will be in the SI, which is kilograms. So the value of the mass is given by 0.15 kilograms. And by this, we need to rewrite this statement correctly. So the mass of S is M is equal to 0.15 kilograms. Okay. Then this is it for this exercise. Let's move to the next exercise, which is exercise number 5, section 7. Then in order to determine the force constant, spring constant K of a spring of negligible mass, we fix the extremity A of the spring and we connect to the free extremity a solid S of mass M is equal to 20 grams. Knowing that the grams is not the SI unit of mass, in order to convert from grams to kilograms, we simply divide by 1000. Then 20 divided by 1000, this is equal to 0.02 kilograms. And the spring hangs vertically, see document 1. They mentioned this document, now we can use it. Now in number 1, okay, before we refer to this exercise, let me say the following. So here, okay, we have that G is equal to 10 newtons per kilogram. Also, let me say that in the previous exercise, G was not given to be 10 newtons per kilogram, so please add here that take G is equal to 10 newtons per kilogram, because this is always given. And this reflects the planet on which we are performing the experiment. So now in this case, because the value of G is given in the exercise and we know the mass, we can directly determine the weight. Then let's recall that the aim of this exercise is to determine K. So knowing M and G, one can directly determine the value of W. Knowing W, using the condition of equilibrium, one can determine the tension T. Using Hooke's law, one can determine the value of K. Okay, now here in number 1 they are telling us name the forces acting on us. Then the different forces acting on us, we have the weight because it has a mass, and because there is a spring, then it will be submitted to the tension T. And in the same part they are telling us tell for each of these forces whether it's a contact force or force acting from a distance. We know that the only three forces acting from a distance are the weight, the electric, and the magnetic, so this is acting from a distance. And all other forces are classified as contact forces, and in particular the tension T. Now in number 2 they are telling us the solid S is in equilibrium. This is extremely important, which means that at any moment in this exercise we can use the condition of equilibrium. Now in 2.1 they are telling us give the condition of equilibrium. So as a title we will write at equilibrium. Then on the left hand side of this equation we'll write the different forces acting on the solid S, and they are given by the weight and the tension. And on the right hand side of this equation we'll write the zero vector corresponding for the condition of equilibrium. Now dragging T to the right hand side, we will have that W vector is equal to minus T vector. Now here no need to continue and discuss in magnitude or anything regarding the properties of the force, because they are simply asking us for the condition of equilibrium. Now how do we read the first equation? That the effect of both forces acting on the solid S cancel each other, whereas the second equation means that both forces have the same line of action, opposite direction, and same magnitude. And this is extremely important, which reflects the fact that in physics, whenever we rearrange the equation, it gives different physical significance. Okay. Now in number 2, they are asking us to determine the magnitude. So always one must directly think of G and the mass, which allows us to determine the weight. Knowing the weight and the condition of equilibrium, one can deduce the tension. So we are interested in determining the magnitudes of each of the forces, which means that we need to determine W and we need to determine T. Then let me say that W vector is equal to minus T vector. Then extracting from this relation the relation between the magnitudes. So in magnitude, now we drop down the vectors and we remove the minus sign, then W is equal to T. But we know that the value of W is equal to 0.2 newtons. Then the value of the tension is equal to 0.2 newtons. And by this we have determined the values of each of the forces. Here I repeat that we have used the condition of equilibrium because they have stated that the solid S is in equilibrium. Now in 2.3 they are telling us to represent these forces on a diagram. So first let me sketch again the solid S. And this is the point G, the point of application of the weight, and this is the point B, the point of application of the tension. Then now we need to represent these forces. We are talking about the weight and the tension. Here in the question they didn't specify any scale, because we know that in order to represent the forces we need to determine the length of the forces. In this case we know the magnitude, and the connection between the magnitude and the length is the scale. So here the scale is not given, so we are free to choose any length. Suppose that I will choose it to be 2 centimeters. What is important that W and T must be represented using this at the same length, using the same or equal length. So this is the tension T. Notice that I have represented T 2 divisions, then the weight. then I will represent the tension with 2 divisions. Then this is the weight having a magnitude of 0.2 newtons represented at a certain scale, and this is the tension T represented using a certain scale and having the magnitude 0.2 newtons. Now what is important here is that T is represented respecting its properties, which is vertically upward, and the point of application is B. W is represented vertically downward respecting its properties, in particular the point of application is G, and respecting this relation, which is weight is equal to minus T vector. Both of them have the same line of action, opposite direction, and same magnitude, which is the same length. Okay, the point of application is not important because this doesn't tells us anything about the point of application. Let me make some space here. Now in number 3 they are telling us the solid S is always in equilibrium, the elongation of the spring being 5 centimeters. Then the value of delta L is equal to 5 centimeters. Knowing that the centimeters is not the SI unit of measure of a length, in order to convert from centimeters to meters, we need to divide by 100. Then 5 divided by 100, this is equal to 0.05 meters. Now we know the elongation, and we already know the stiffness, we know the tension T of the spring. This will allow us to calculate the force constant K using Hooke's law. Then here, the elongation is not denoted to be X or delta L. We are free to choose the notation of the symbol of the elongation to be X or delta L. I have chosen it to be delta L. Then T is equal to K multiplied by delta L. You are interested in determining the value of K. Then constructing the triangle T, K, and delta L, covering K with our hand, then the value of K is given by T over delta L. The value of T is given by 0.2, and the value of delta L is given by 0.05. Plugging this fraction on the calculator, then the value of K is given by 4. Since T and delta L are expressed in the SI given by Newton and meter, the value of K is given by Newton per meter. Then the value of K is given by 4 newtons per meter. And now let's move to the final exercise of this part, which is exercise number 6, section 8. The object of this exercise is to determine the stiffness K of the spring. Then before we discuss this problem, let's consider it overall. We are interested in determining K. K can be calculated using Hooke's law. We need to have X and delta L, X and T. We have the value of X, but we don't know T. T is related to W because this is at equilibrium. The weight can be determined using M multiplied by G. The moment we know the weight, we can deduce T. Knowing T and X, we can determine the value of K. Of an elastic spring R is suspended vertically with its upper end O fixed to a support. Its lower end A carries a solid S of center of gravity G, and of mass M is equal to 0.5 kilograms. Now the solid S is then submitted to two forces, its weight W and the tension T of the spring. For sure they are discussing document 1. At equilibrium, so this is at equilibrium. At any moment in this exercise we can use the condition of equilibrium. The elongation is given by X is equal to 10 centimeters. Knowing that centimeters is not the SI unit of measure of length, so in order to convert from centimeters to meters, we divide by 100. Then 10 divided by 100, this is equal to 0.1 meters. Given that the G is equal to 10 newtons per kilogram, which reflects the fact that this experiment is being performed on the surface of the Earth. So I repeat, overall we know M and G, we can determine W. W is equal to T because in magnitude, T will be given by Kx, then Kx is given, we can determine the value of K. Now indicate for each of these forces if it's a contact force or force acting from a distance, we know that the only three forces act at a distance are given by the weight, the electric, the magnetic. And all other forces are classified as contact forces, and with no exception, the tension T is one of them. Now, as for number 2, indicate the point of application, the line of action, and the direction of W. And we need to list them in the Pilgrim order, which corresponds to the following order. Then let's start by the point of application. Line of action. And the direction. So the point of application, we know that because it's acting at a distance, then the point of application will be the center of gravity G. The line of action is vertical because the weight always acts vertically downward, and the direction is downward. As for number 3, they are telling us to calculate the magnitude W of the weight, which is given by M multiplied by G. The value of M is given by 0.5. And the value of G is given by 10. This is equal to 5, since both M and G are expressed in the SI, so the value of W will be in the SI, which is in newtons. And recall that this can be determined from, this is kilograms, this is in Newton per kilogram, and eventually they cancel out. Then the weight is equal to 5 in newtons. Now in number 4, they are telling us show that the magnitude of the tension is given by 5 in newtons, because we know that the weight is 5 in newtons and this is at equilibrium. So at any moment in this exercise we can use the condition of equilibrium. Then let's write at the title at equilibrium. Let me do it here. Then on the left hand side of this equation we write the different forces acting on the solid S given by the weight and the tension, and this is equal to 0 vector. Now dragging T to the right hand side, this will be given by the weight is equal to the minus tension. First equation tells us that both forces acting on the solid S cancel each other, whereas the second equation tells us that weight and tension have same line of action, opposite direction, and same magnitude. So this part will be the answer for the condition of equilibrium or the vector relation. Since they are asking us about the magnitude of the tension, so we need to extract from this equation the relation between the W and the tension at the level of the magnitudes. Now let's say in magnitude, that the weight is equal to the tension, but we know that the value of the weight is given by 5 newtons. Then the value of the tension is equal to 5 newtons. Now after we have determined the value of the tension and we know the value of the elongation, so recall that here we are in the case of the elongation, the value of K can be determined using Hooke's law. Then apply Hooke's law. Hooke's law is given by T is equal to K multiplied by X, and we are interested in determining the value of K. Here I am using the same notation because elongation is being denoted by X. Constructing the triangle of this formula. Here, because we have multiplied, then T will be at the top, K and X at the bottom. We are interested in determining the value of K. Then K is given by T over X. The value of T is given by 5. And the value of X is given by 0.1, which is equal to 50. Since everything is expressed in the SI, then this will be expressed in the SI, which is in newtons per meter. Then the value of K is given by 50 newtons per meter. What does 50 newtons per meter represent? It is the stiffness of the spring. In other words, in order to compress or elongate the spring by 1 meter, we need to exert a force worth of 50 newtons. So that's it for me in this video, guys. In part 3, we'll complete the explanation of this chapter and solve more exercises.